So this will be a little bit further on than our normal nomenclature because we're going beyond the covalent nomenclature, which you can still use, but we're adding in organic. So what is organic? You hear about that a lot. Organic does not necessarily mean healthy. Benzene C6H6 is organic, but it is a carcinogen and it's toxic. So you would not want to have that as something to consume. Organic simply means carbon-based molecules, and these are the elements that you will find in living things, and that's back to a middle school standard. So hopefully you remember CHOMPS as a way to remember carbon organisms, eat things. You just change that M for an N to remember what it is. Electron dot of carbon. Carbon is in group 14. There goes group 14. So it has 4 valence electrons. 1, 2 in the S and 1, 2 upspinning in the P block for a total of 4. So it has 4 electrons that can reach out to share with some other compound. So this guy can become 4 bonds. Okay, it could be 4 single bonds. It can be 2 double bonds. It could be 1 single and 1 triple. Okay, so lots of different variations there. It could be 1 double and 2 single. Lots of variation. That is why we're carbon-based life forms, because we have so much variety that we are able to bond with. Okay. Now, long chain hydrocarbons we've used already before. CXHY, we've done hydrocarbon combustion. Long chain hydrocarbons just means we have a lot of carbons in there to make a super long chain. And so we focus a lot on what's going on with the carbon. Like this, they are nonpolar. Okay, so anytime you have a base hydrocarbon, those guys are nonpolar. But if you add any accessories like chlorines or fluorines or oxygens, nitrogens, phosphorus, sulfur, then you can be adding in some variety, which makes it polar. So, and that's the quick check reminder for polarity. And there is some reminders again. Notice for the halogens, when we're doing naming, you would use chloro and fluoro instead of chloride and fluoride, because in organics, we're concentrating on the carbons. And then we have accessories of the halogens or oxygens or hydroxides, any sorts of variations like that. There's more that are just not listed there. So when we draw these structures, methane is the name for CH4. So here is our drawing of methane, nonpolar, because it has no lone pairs and all the outer atoms are the same. So it is completely balanced, just London dispersion forces. Trichloromethane, 3 chlorines on the methane. So you take out 3 of the hydrogens and you add in chlorines. And that is how you get trichloromethane. So you can probably guess how to get monochloromethane and dichloromethane. Although a lot of times we don't say monochloromethane, we just say chloromethane. Trichloromethane has 3 chlorines. Notice there's no dots on here. And that's because in organic, you don't have to put the dots, because what are we concerned with? We're mainly concerned with carbon. So that's another thing that you can do. For you, when you're doing all your drawings, though, do make sure you have all the unbonded electron pairs or lone electrons. Make sure they are on the drawings or you do not get credit, because you are trying to look at it for other reasons. But in true organic, you would be taking off those dots. Okay. Ethane has the formula C2H6. So there's no central atom. This is the smallest chain of just 2 carbons with the hydrogens going around it. carbon has 4. So organic is fun because you're always counting to 4s. As long as you can count to 4s, you can usually figure out pretty much everything as long as you have written down what each definition means. Carbon always has 4 bonds. So you always go through and double check that everything around the carbon adds up to 4. And then you're pretty secure that you did put the problem together. Now, we're not going to go into all the definitions. We're only going to just do a couple. There's a whole bunch. Single bonds, though, you already know that definition. That's when you have 2 electrons that are sharing, creating a sharing bond, 1 electron from the left carbon, 1 electron from the right carbon. In organic, this means it's hydrated and saturated because it's full of hydrogens. There's a hydrogen that can go on every single one of these spots. So it is saturated. If one of these was a double bond, then we would have less hydrogen. So if the bond between the carbons was here, we would lose 2 hydrogens. That's not saturated anymore. That's more dilute. Okay, so that's how you kind of keep track of these things. When we have a saturated one, we have a special suffix of ane. Okay, so that is how this guy ended up on the last page being called ethane, because everything is a single bond. And methane, everything was a single bond. How about if you have a double bond? One double bond changes your suffix because it's now not saturated. A double bond is when you have 2 pairs of electrons that are bonding, 2 from each side are bonding together and sharing. This suffix is ene, E-N-E. Always happens with only 1 double bond shown. You just need 1 double bond shown to be an ene. And a triple bond, same process. 3 electrons, those white electron dots are for the left carbon. These yellow electron dots are from the right carbon. That's giving you a triple bond. I will just draw in here real quick. 1, 2, 3. Okay, and that is what makes it a triple bond. This item on the right is just shown so you can tell what it looks like when you break it down. But at this point, you should be drawing everything as the left side is. Bonded electrons always should have bars, not dots. And this suffix is ine, Y-N-E. So prefixes. Here's your list of prefixes. If it's methane, it's 1 carbon and all single bonds. Ethane, 2 carbons, all single bonds. Propane, 3 carbons and all single bonds. How else would it be? Oh, well, there's no methane. Ethene, 2 carbons with a double bond. Ethine, which is usually called ethylene. That one would be 2 carbons with a triple bond. So you need to remember this order. Now, from 5 on, it's pretty obvious. It goes by the way geometry does, pentagon, hexagon, etc. The first 4 people get confused on. So the rule is me eats peanut butter. Yes, I know it's silly, but it is a way to remember that order. Me eats peanut butter, to give you that for the first one. So this picture here is ethane, 2 carbons with all single bonds. Now, what am I not showing on here? I'm not showing the hydrogens. Okay, you could show all the hydrogens. So ethane technically has a hydrogen on each one of these little stalks that are coming out. So this is how you'd be used to seeing ethane. Eth, 2 carbons, ane, filling up with hydrogens. 1, 2, 3, 4 bonds for the left carbon. 1, 2, 3, 4. So now we know this formula would be C2H6. So you can always draw it, fill in the hydrogens, and that is how you would come up with your formula. There is also an equation you could use for that. In organic, we often do not show the H's. So as long as I show the little stalky thing, I know there's an H attached to it. Those are all alkanes. Isn't that nice when we name a group? So we have organic, which is all the chunks. And then the alkane group is all the hydrocarbons that are saturated, all single bonds. So its group name is alkanes. And there's the formula for finding it. So you can use that for a formula, or you can just draw it for the formula. So let's try it. If I have 5 carbons, using this formula, then I have 2 times 5 plus 2 to get the number of hydrogens. C5H12 would be the formula for, let's think, 5 carbons, pentagon. Pent, ane, because they're all single bonds. Alkanes are all single bonds. So this guy's name is pentane. Okay. What if you have 10 carbons? Okay. Same formula, because it's only for the alkane group. It's saturated. And that's decane. Okay. So how about propene, which is more accurately 1-propene. There's a couple of different ways that we've learned how to name things over the years. So it took a little bit of time for us to come to consensus, but we can still do everything we did before. Pro and ene. What did ene mean? 1 or more double bonds. Pro, me eats peanut butter. It's the third one. So we have 3 carbons. Now this guy tells me that I have a double bond at spot 1. So that is the additional thing. Spot 1, double bond. Okay, 3 carbons, 1 or more double bonds. So I'm putting the double bond in this case in spot 1. And then what do? Fill in with hydrogens. How many do I need? I need to have 4. This left carbon has 2, so he'll need 2 more to make 4. The center carbon has 1, 2, 3 bonds, so he only gets 1 more. You can put that on the top or on the bottom, either way, because overall it doesn't matter, which I'll explain in a second. That last carbon only has 1, so he's going to need how many more? 3 more, because carbons always have 4 bonds. So this is the setup for propene. Now, what's different about this? When you're plugging these ones in, you're counting to 4 each time. This spot here is the first carbon-carbon bond, so that's why it got to be a double bond. However, I could also draw it with the double bond on the other side. I just got to rearrange where those hydrogens are. Does it still make sense? 1, 2, 3, 4. Yep. 1, 2, 3, 4. Yep. 1, 2, 3, 4. This is just the mirror image. The molecule doesn't know if you're looking at it towards the screen or you're going around the other side and looking at from him that way. So this guy is also spot 1. So you can start counting left to right or right to left. You can put the hydrogens on the top or on the bottom. And there's a couple more rules to make it a little bit more intricate later, but that is the basis. After I have this drawn, then I know the formula. 1, 2, 3 carbons, and 1, 2, 3, 4, 5, 6 hydrogens. Oh, look, is that a pattern? It is a pattern. It's 2 times N for enes. Look at this guy. This is also propene. It doesn't look like it at all. What you do when you see it in this really shorthand form is when you get to a bend or the start or end, you count that as a carbon. How many carbons? 3 carbons. The first carbon has a double bond. The second carbon-carbon bond is single. We don't even write even the little sticky things of the hydrogens on these ones because we don't need to. We know we will always fill in with hydrogens unless said otherwise. So if you have something that looks like this, yes, this can be a carbon chain. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. C11, H24 if it's an ane. C11, H22 if it's an ene. So quick and easy once you learn the system. At first you're like, whoa, there's so many key terms. But once you find the flow, this is actually a lot faster naming than anything else. And then you can get into the fun stuff. Okay, so 2-hex-ine. 2-hex-ine. Spot 2. Hex, 6 carbons. Ine, double, or not double, ine, triple bond. So in spot 2, there is a triple bond in hex-ine. First thing you draw, your 6 carbons. Then in spot 2, you put the triple. So this is spot 1, this is spot 2, spot 3, spot 4, spot 5. Notice it's always between the carbon-carbon. Why? Hydrogen can only do a single bond. So we don't have to specify if he's an ane, or ine. He only ever can do anes. Now, can we write this from the other side? Absolutely. This would be spot 1, spot 2, spot 3, spot 4, spot 5. So either way, you'd either have the triple bond here or you'd have the triple bond there. 2-hex-ine. Oh, and did I check? Let's double check. 1, 2, 3, 4 bonds for that carbon. 1, 2, 3, 4 bonds for that carbon. 1, 2, 3, 4 bonds for that carbon. 1, 2, 3, 4 bonds. 1, 2, 3, 4 bonds. 1, 2, 3, 4. Lots of silly, easy counting. But now I know that this is correct. So I could add up the C's and add up the H's to give me my CXHY or my long chain hydrocarbon. Hydrocarbons with no accessories are always nonpolar. This guy is not considered saturated because he has the triple bond. Those bonds could have been used to place more hydrogen. So he's not saturated. He's more dilute because he does not have his fill of hydrogens. What if there was a triple bond in both of those locations? We would have to lose some of our hydrogens. 1, 2, 3, 4. So this hydrogen and that hydrogen would be lost on the next carbon to the right. 1, 2, 3, 4. So those 2 hydrogens. But then that guy would be 2,4 dihexene. So you add a little number in there to say we have 2 triple bonds at spots 2 and 4. So that was a really, really, really quick overview of what we are doing with organic. So I'm going to put up the exit slip. Why is it not letting me stop?